Okay, so first of all, there's these forces out there that we can't get away from. We got forces forces a push or a pull, and they make things accelerate, right? Not just a force, but a net force. That's what Newton's second law tells us. Newton's second law says that there's a net force that makes things accelerate. Not just a force, but a net force. So you have to add up all those forces to decide. Well, there are other forces out there besides field forces and contact forces. There are other forces, and the number one force is weight. Okay? All right, so the force due to gravity is a vector quantity. The direction is towards the center of the earth. Okay? The magnitude of the weight is calculated by mass times gravity and is dependent on your location, because the further gravity is a field force, so the further you get away from Earth, the different amount of gravity would act on you. Now, it's not very much difference, but if you go to the top of a mountain, you would have a little less gravity. If you went to the bottom of the Grand Canyon, you'd have a little more gravity. I'm trying to talk to y'all. Next, normal force. For every force, stop, refocus your attention. For every force, there is an equal but opposite force. Well, if the earth pulls on you, then you got to be pulling on the earth. There is an equal but opposite force, and that is the normal force. Now, technically, equal but opposite in terms of the other action-reaction pair. So, earth pulls on you, and you pull on earth. You pulling on earth is not the normal force, but it is the force that acts in opposition to that. You'll see more what we mean when we write up on that. Now, by definition, the normal force is perpendicular to the surface. You see in this diagram here, force normal is perpendicular, or 90 degrees, it's drawn, try that again, is drawn 90 degrees to the surface. So force normal, 90 degrees. So when we come over here and we look at this force, this box that's on an angle, we see that the force normal is no longer opposite the weight. The force normal is now at an angle, but it's still 90 degrees to the surface. Okay? Force normal is a force opposite gravity that is always 90 degrees to the surface. So force normal can be given by this formula here, mass times gravity times cosine. And it has to do with how the vectors were drawn there, and I'm not going to take time to go through that at this. I don't really like to use this angle. I like to think of force normal in different scenarios. All right? So we're going to look at some of those scenarios now. Force normal. Every force, the number one force that we can't get away from is weight. If there's a force that's equal and opposite, there's got to be opposite our weight, and that is basically where we run into force normal. Technically, it's not equal but opposite to the weight, because opposite my weight is me pulling on earth. Okay? But it is a reaction to that. So when this box pushes on the table, when these objects are pushing on the table, what's the reaction? Table pushes on the box, right? What's making this weight, or this foam, what's making this foam push on the table? Gravity. So gravity gives this object weight. The reaction is the table pushes on the weight. The table pushes on the weight is force normal. How much force does it push with? Okay, so that's what we're going to look at. So start off with, what happens to the force normal when you change the angle? All right? Ready? Back on track. Let's think about how force normal changes as we change the scenario. So we see in this diagram that as the angle increases, the whole diagram, as the angle increases, the force normal eventually reaches zero. So let's think about this scale we have right here. So we got this scale up here. How does this scale behave? What does the scale measure? Weight. Okay, so this is the thing we're arguing. The scale is not measuring the weight. What is the, okay, good, mass. Not measuring mass either. Mass is measured by balancing objects. Spring scales would measure weight, but technically they're not measuring weight. They're actually measuring the normal force. So think about what's happening here. The weight is pushing down, and the spring scale is pushing up. If this spring scale does not push up, then what does this object do? It goes through the scale. It falls down and collapses, right? So how hard is this pushing up? The same as the weight. Case number one, when you're on a level, flat surface. Case number one, when you're on a level, flat surface. We're not going to sort these right now, but in case number one, when you're on a level, flat surface, the weight equals the force normal. Okay? Go back to here. When you're on a level, flat surface, the force normal is equal but opposite the weight. How much does this weigh? Well, according to this scale, it weighs 20. What is the force normal? How much force is this table pushing with? The same amount of force. Check? Okay, now, let's talk about changing force normal for just a second. What happens to this scale if I pull up on this a little bit? The weight changes. Okay, that's my point. Does the weight of this object ever change? What is the weight of an object? How much gravity pulls on it? Am I changing gravity? What's happening to the... right. Am I changing the weight of the object? No, but is the table pushing as hard? So I wish we had this up on the screen so you could see. It would make it a much bigger point. I think you get the idea from where you are, but it's still better teaching if you could see the number. So Ms. Conley, as I pull up on this, is it still pushing on the table? But it now reads 18. I pull up a little more, 15, 10, 5. Now it goes to 0. Why is the force normal now 0? Because there's no weight being applied to the desk. Okay, so case number one. When you're on a level surface, what does the force normal equal? The weight of the object. The force normal is not the weight, it equals the weight. If this is 20, and Mr. Harn pulls up with 10, what's the force normal now? 10. Because it's got a total 20. Yes? Let's make this little diagram real quick here. So, we have our table. Sitting on the table is some books or a weight. Okay? So we have sitting on the table those weights. What pulls down? The weight. What's the weight equal? Mass times gravity. There's another force acting opposite this, and that is, what else is happening here? The table pushes on the box. Table on box. Or the weight, whatever. Yes? If those are equal but opposite, then the weight stays as it is. Is that true for this situation right now? Is this staying as it is? Is it moving up or down? No, it's good. So the weight must equal the force of the table pushing up. If the table pushes harder than the weight, then the weight will start to move up. If the weight pushes harder than the table, then the weight breaks the table. So they got to be equal. So if the weight is 20, then what's the box? Or excuse me, what's the force normal? Which is the contact force between the two objects. It is 20 newtons also. Now what if Mr. Harn comes over here and pulls up on this a little bit? Is the weight of this object changing? No, I'm not changing to 20. But does the table have to push as much? No, because now there's Mr. Harn pulls up with 10 newtons. So down 20, up 10, that must leave what force normal? 10. What happens when you pull up on an object? The force normal is going to be decreased. Check? Okay. Now, y'all ever did that little trick to your sister or your mama when they get on the scale and you reach over there with your foot and you touch the scale? You never done that? I think that was a sarcastic, yeah, I don't like that, because it's a good trick.
I did.
Okay, good. You should try that trick sometime. Make them weigh more. Did you actually make them weigh more?
No.
You made their force? Yeah, say it, class. You made their force normal go up. But you didn't make them weigh more. How did you make their force normal go up? So remember, what is this scale measuring? Mr. Zach? This way, please. What are you making this scale measure? We lost something. Scale doesn't measure weight. Scale measures force normal. Good. Stop. What does this scale measure? Force normal. What is force normal? It's the force acting opposite gravity exerted by objects like desks. Or you. Maybe you exert a force normal if you push on something. Check mark? Make sure we're clear on that. For every force out there, there's equal but opposite force. Weight's pulling on this object. There's got to be something pushing against this object. What's pushing against it? The table's pushing against it. That, how much force does the table exert? The same as the weight. When it is level. What about now? Is the table pushing as much now?
No.
Because I'm actually doing what? Subtracting from it. Yes? Okay, now go back to my... You ever made your mama pretend to weigh more? Somebody said, yeah. What's the force normal now? Anybody? This is why I wish y'all could see this number. So now the force normal is like 100. How did it get to 100? Because I didn't change the weight of these objects. You applied more force. So if I put more books on this thing and I stack this thing up with stuff, force normal goes up. The weight of the object doesn't change. But if I push down with 10 newtons, the force normal now goes up 30 newtons. Case number one. Case number one, when you're on a flat surface, what's force normal equal? The weight. Case number two, we pick up on it just a little bit. Force normal is going to go down. If we stack more stuff on it or lean on it, force normal goes up. Check mark? Okay, now, force normal has to exist. Okay, let's choose a lighter weight object besides this. I wanted that one to start off with. That fell out of something. Okay. I just got a brand new one of those. I don't need to break it. Let's go with this marker. Okay. All right, ready? Angle. Case number one, level. You can either be pushing down, force normal goes up, or you could be pulling up, force normal goes down. What's the force normal now? Equal to the weight. How much force is between the scale and the marker now? Zero. The force normal is now 0. Okay, so, excuse me. If this is maximum and this is 0, then what's the force normal right here? Some number between the maximum and 0, agree? How would we calculate that? Well, that takes into account the angle. Okay, we'll look at that. Other thing that's happening. What is some of the what's giving us force normal right here? Gravity. Why does this marker slide off this? No, why does it slide?
It has more force than the friction.
This is true, but what's exerting the force that makes it slide? Let's try this object. Why is this object not falling?
Friction.
Is there a force trying to make it fall?
Yes.
Or what's trying to make it fall?
Gravity.
Gravity's trying to make it fall. What's the force keeping it from falling?
Friction.
The force normal applied by the scale, which is equal but opposite. Why does it start to slide? That's true, friction isn't greater, but what's making it move? It's not level. Am I pushing on it? Well, what's pushing or pulling on it?
Gravity.
Gravity. What is happening in this case? Gravity's pulling it straight down. What is gravity doing now?
Going at an angle.
Going at an angle, you see it? So, in this case, the weight is force normal. In this case, the weight makes it fall, and force normal equals 0. In this case, the force, some of gravity makes it slide, and some of gravity pulls it into the table. Yes? Try one more time. I think we're there. What is gravity doing right now? Pulling it straight into the spring scale. What is gravity doing now? Pulling it straight down. What about at an angle? At an angle, some of gravity pulls it into the spring scale, and some of gravity pulls it down. 2 parts, 2 vectors, so forth and so on. All right. Okay, now. That's what I'm just trying to explain. What's the number one force we can't get away from? Gravity or our weight. The weight, force due to gravity. Now, at an angle, some of gravity does what? Pulls it down the ramp. This is force applied due to gravity. What else does gravity do? Some parts of gravity actually push the box in contact with the table. This is force of gravity on the table. Okay? Yes? Gravity, the resultant, has 2 parts. Some parts of gravity pull it down. Some parts of gravity pull it into the table. See the red vector? The red vector becomes what we know as force normal. Okay? Y'all with me there? Now, if this is the angle, is this an adjacent leg or opposite leg? That's an adjacent leg. What trig function uses the adjacent leg? Cosine. So, when a box is at an angle, the force normal equals the cosine of the angle times the weight. And the weight is mass times gravity. Okay? All right. What is force normal? Force normal is a force that goes opposite the weight in normal circumstances. You know why you thought this weighed you? Because they built this to measure force normal, and they designed it to be on a level surface. And on a level surface, the weight equals the force normal. Now, if you want your true weight, don't be adding weight to it, because that makes the force normal go up. Now, what you could do is you could come and lift up on somebody, and the force normal would go down. Or if you want your force normal to go down, weigh yourself on an angle. If you weighed yourself on an angle, would the force normal go up or down? Remember, right? This is 0 force normal. This is maximum force normal. So as the angle increases, the force normal decreases. Okay? All right.